I'm going to explain how LCA works. No, how to find LCA, which is lowest common ancestor. We're going to use doubling and binary search. So this is root, and I've scribbled this ridiculous graph. If you have what if you have you wait you if you have u and v, and if you want to find the common ancestor, which is here, of these two nodes, then we're going to firstly move the u up to this here after this node by holding information about the distance from root. For each node, you have information, the depth information from the node, and you compare these two nodes. The depths are one. The difference, the gap between two, the gap of the gap of these two nodes depths are one. Therefore, you're going to make them same. So you make it go up to this node, and after that, you don't know this is the LCA. So you're going to solve it. Firstly, Dublin. I'm going to use Dublin, which is um, you're going to know the parents, his parents, no, his ancestor, um, his ancestor whose distance from the node is 2 to the power of 0, or 2 to the power of 1, 2 to the power of k. You can so firstly you know the you will have, I think, 2 k minus 1, and like this, 0, 1, 2, 3, boom, 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 and the size of the nose, it stands for vector. No, vertices, yeah. So the parents of 0 should be minus 1. Parents of, so let's say this is 1. The parents is 0. This is um the first ancestor of him. So let's say this is 2, then the parent is 0. Let's say this is 3, then his parent is 1. And 4, 5, 6, 7, then 4, 5, 6, 7. 4's parent is 1, 5's parent is 4, 6's parent is 5, 7's parent is 4. Then you're going to look, um, okay, so firstly, the parents, I want to make this vector, I mean matrix, ki, uh, when you look at a node whose index is I, for example, here, I is 3, and K is the number of the, how do you say that, power? Is it power? Exponential? Exponent, yeah, exponent. I think it's exponent. Yeah, exponent. And this is base. So base and exponent. So I want to make this matrix. This is going to be like this. So in order to make the next index k plus 1. Oh, oh, yeah, it's really hard to draw. It is created by the previous. Okay, previous ki. No. So let's see how it works. Parent k. What was that? Parent k. Oh, I forgot. Oh, this is I. So what it says is you have, I think 2k, yeah, 2k, 2 to the power of k. It's parents, you have it here, and from that node you're going to look at the 2 to the power of k, it's parent, and you can like multiply them. So what I'm saying is, it's, I know, difficult. So for, let's say this vertical straight line of nodes, then they, let's say they are directly connected. It's so hard to see. So they're connected as a parent and child, and the root is here. Oh, root is here. So if you say this is I, you're watching here, and you can you can firstly solve. So for example, 1 0 1 2 3 4 5 6 7. So this is 7, this I is 7. And though, so here should be, now for example, if it's 6, 7's parents is 6. So parents, if you say here, if you use this, parents 0 7 equals to 6. Yeah, 7's, the first parent should be 2 to the point of 2 to the power of 0. The parent is 6. And I mean 2 to the point, 2 to the power of 0 distant away from the node, 2 to the power of 0 distant away from the node. Yeah, ancestor. Yeah, so next we can find this value, which is 2 to the power of 1, 2 to the first power. So it should be 5. And firstly we solved this. The next is this, using this. So 2 to the first power, wait, 7's ancestor, one of the node 7's ancestor, who is 2 to the first power distance away from it, we're going to solve it. We're going to find this this node by using this. So now we have I equals to 7, k plus 1 equals to 1, because what we solved already is 0, k equals to 0. So we have parent 0, 7, which is 6. So the whole thing is 6, yeah. And k is 0. Therefore, you already have this path. It's not a path, so it's not a path though. So you first line in first repetition iteration, you've already solved who is the first parent of 6. Therefore, you can use this. So so in order to solve who is the ancestor here, you can use this and this. So which means, so I think it's easier to understand the next time. So when you solve this, you have already this line and this line. So you can use, ooh, so then firstly the I is 7, but next time I'm going to use this as a k. Therefore, this is 1, and k plus 1 should be 2. So we're going to use 1, 1, 7, 2 to the power of 1, 2 to the first power. So this says the distance is 2 to the power of k. The next distance is the 2 to the power of k. Oh, I'm sorry about that. It's not. Sorry about that. It's not that like that. It's plus. The distance should be added. Distance, yeah. Two distance are added. The half distance are added to the whole into the whole distance. So this is Dublin. And what I was struggling to understand was not this one. Oh, it's so hard to write them, like obliterate it. Bolt out. Bolt out is like, bolt out is not bolt, blot out. Blot out is like make it black. No, blot out. Oh, that should be this the meaning. But it's kind of hiding things. Okay. Also erase the memory. Let's blot out it out of your, blot out it. Um, blot something out. Blot this memory out. I don't save it. So that was Dublin, how Dublin works. And when we if we find ancestor, as I said, firstly we have u here and v here, then you're going to move the u up to here, which is the same distance away from x as v. So, but yeah, so you have a lot of you have a lot of nodes, a lot of nodes here, and you're going to find this one, the lowest common ancestor. So how do you do that? You can move 2 to the point of 2 to the power of 0 and you 2 to the power of k. How to use that? So firstly, 2 to the power of k, which is the maximum k you can have. So it can be above the root. So if it's over above the root, it can be -1 or infinite number or something else. And then you don't do anything. Next time you will look at 2 to the power of k minus 1, which is the half of the previous one. Then um so so you look at the distance from no. So you're looking at the ancestor of those two nodes. So let's see, it's difficult. So if you have oh, 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 be here, then if the ancestor is here that you look at, is if the ancestor you're looking at is here, the both ancestors here, because you're looking at the parents who is distant 2 to the power of k minus 1 distance away from u and v. They're the same, but once you come below here, the border, which means, for example, u's parents is here, v's parents is here, then they're different. Therefore, you can find that it is below the LCA. Yes. So you're going to do it. Firstly, go to the top, and next the half, and you're going to come below the border. And after that, so for example, there are a lot of nodes and parents here. So if you look at the node here, so for example, UV here, and if you look at this node, which is just above the LCA, you're going to, it should not be U or V. U and V are below here, and there are lots of nodes here. And if you look at this, and this is LCA, just if you look at the node just above the LCA, then you're going to look down to, like for example, 2. If it's 2m, you're going to look at 2m minus 1 next time. And they are different. Use parent, use ancestor, and these ancestor are different now. Therefore, you need to go up again. So then, what's gonna happen? Then Firstly, you know the distance. This distance is 2 to the power of n minus 1. You know, of course, the distance from this border to u and v is also 2 to the point of minus 1, 2 to the point of n minus 1. So this is the half. So this is also 2 to the point of n minus 1 distance away. And therefore, you're going to look at the half border, the border that divide their area into half parts. So this distance here should be 2 to the point 2 to the power of n minus 2. Yes. So what's gonna happen? You divide the area every time into half. So finally, even even when knows a lot, there's large number of nodes. You're going to divide it into half and half and half until the LCA's next LCA's children are found. UV. So once you find, oh, this is below the LCA. Once you find it, you're going to move the U to the ancestor. You move the V to its ancestor. So this is how LCA is found. So struggling with explaining, but I'm going to improve it